Okay, so today we're going to continue on with our discussion of the Kepler problem. Again, we're still thinking about an arbitrary central potential energy, U of R, but it is a central, or it gives rise to a central force. We're going to look at some general expressions for how to calculate the orbit under a general central potential. Look at a few time-dependent parameterizations of both the radial direction and the angle. Remember, we already showed that the motion is going to lie in a plane. And then we'll go ahead and look at a convenient transformation that you can do on this to write kind of the most compact version of the differential equation that governs the orbit, the Binet equation. So let's start by looking at what we had last time. We said that the total energy, and that's the total mechanical energy of my system, which has been reduced from a two-body system down to an effective one-body system. That's why this R here stands for the separation between the two bodies, and this mu is the reduced mass. So we're still using mu. In a lot of problems, the central object, might be the sun or something like that, is so much more massive than the object that's doing most of the moving that mu is pretty much just the mass of the moving planet. But I'm going to leave it general for now and just remember that mu is the reduced mass. And we said that our kinetic energy basically has two terms. There is a piece that comes entirely from radial motion, that's in and out away from the center of mass, or really, I guess, the distance between the two particles. The second piece came from the angular motion, and we rewrote that in terms of the conserved angular momentum. So as a reminder, L is the angular momentum of the system. It's mu times that R squared times phi dot, where phi is that angle that the reduced mass is making with respect to some polar coordinate system. Notice, though, that this piece actually does not have like an explicit time derivative in it. L is a conserved quantity. And that kind of means that this looks like it's just a function of R, which means we can often group these two together into what's called an effective potential, which is the true potential energy plus this so-called centrifugal potential term. And notice that it's a positive term. It's got a 1 over R squared potential, which is a little strange. Not a 1 over R squared force, 1 over R squared potential. It's 1 over R cubed force. And it depends on how much angular momentum there is. So this is the term that kind of keeps objects from just falling straight into the middle. Okay, this, however, is a first-order differential equation for R. Please note, remember that the R dot is a time derivative. So in principle, there's no problem with just straight up solving this equation for R dot and integrating to get what R is as a function of t. So let's do that first. Okay, so this just comes from moving stuff over, multiplying by the 2 over mu and taking a big old square root. And there's no reason why we can't just separate variables here and integrate directly. Notice this is completely independent of that independent variable time. So we can sort of solve for t of R in a way. Okay, integrating both sides here. It does not really matter what we start our time at, some arbitrary t naught. Usually we'll just call that time 0, but it's totally up to you. And then on this side, we do need to know kind of what the starting position is. There's going to be some sort of constant of integration there, and then we'll integrate up to R. And note all the places that this depends on R. So there's the 1 over R squared that shows up here from the centrifugal term, and of course there's the R in the actual potential itself. The mu and the E and the L are all constants. Now the right-hand side integrates trivially. However, we would need to know something specific about U of R to be able to do the integral on the left-hand side. So for now, I'm actually going to leave it as is. We'll go look at particular U of R's, particular central potentials, shortly, including the famous Kepler problem involving gravity. But for now, at least, this is sort of a solution. Now, whether or not this integral can actually be done in a sort of nice closed form is a question of some debate. It'll turn out, later I'll classify all the different types of power law potentials that give you at least elliptic functions here. Also, whether this integral converges, that can be a particular question sometimes. And then after the calculus, whether or not you can actually invert this to solve for r of t explicitly as a function is also kind of dependent on what this u of r is. So in general, this is kind of annoying, and it only gives me r of t. It gives me what that radial direction is as a function of time. Technically, what it's giving me is t of r, and hoping we can invert it. So maybe this isn't the best use of our time, but at least in principle, it can be done. We might also want to know what phi of r is. What is the angular dependence as a function of time? That comes pretty easily from the second equation, because that's also a first-order differential equation. And separating variables here and integrating. Also lets us do a few things. So on this left-hand side, of course, we're just going to get phi minus whatever that starting angle is. We'll usually say start at the, I don't know, positive x-axis or something, but it's arbitrary. This piece right here, the L and the mu can come out because those are constants. And then I'm going to have to know what r of t is, at least in principle, to be able to do this integral of 1 over r of t squared that comes from up here. Again, we don't even really know if we can get that based on how messy that integral might be. Now, oftentimes we're not really interested in what r of t is or phi of t. I want to know the equation of the orbit. Currently, what we basically get are parametric equations in polar coordinates for the radial and angular positions of my reduced mass as functions of time. And maybe those are important. I mean, those sometimes are relevant. But often we're really more interested in what is the shape of the orbit. I want to know what r of phi is, not r of t and phi of t separately. I want to know the actual trajectory, r of phi. So is there a way we can kind of get around this without having to compute these things involving t and go to some sort of differential equation relating r and phi directly? And the answer is yes. And I want to show you how to do that in two different ways. For starters, we're just going to use the good old-fashioned chain rule. I know that I can rewrite, say, d phi dr as d phi dt, which I know from my angular momentum condition, times dt dr, which is just the reciprocal of this equation. Also, I neglected it here. We guess we should technically have a plus or minus here after taking that square root, and we might have to worry about that a little bit, whether we're talking about the radius increasing or decreasing at some particular time. In general, it's not really going to matter. You can always choose your initial condition to kind of sweep that under the rug. But here, we know what these two things are directly. d phi dt is something that depends on r directly, and dt dr is just this reciprocal. I'll go ahead and stick with the positive sign here. And actually, let's do it this way. I'm going to write another big old root, but I'll have a mu over this. Okay, so this is maybe a little ugly. We might want to clean it up a little bit and pull some factors out. I'll go ahead and just put this L on the outside. I'll bring this mu on the inside because there's a pretty common feature that shows up all the time. And I'll go ahead and separate and integrate both sides. So this will be phi minus phi naught on the left. And then we'll have some integral. We don't really know what our starting point is, initial conditions. The r squared here on the outside of the radical. And then when I pull this in, the mu's will kind of come downstairs, and then we'll be left with our piece involving energies. Once again, not really much we can do here unless we know what this particular function is that we're dealing with. If desired, you can put this r squared on the inside, and then you'll just kind of have three terms that depend on r. Notice the r squared will become an r to the fourth, so there'll be a quadratic term, a piece with r squared u, and a piece with r squared that is a or a quartic term, r to the fourth u and a quartic term. So I don't know if that's really useful. Once again, we've basically gotten this down to, yeah, if you know what u of r is, you can do this integral directly. And this, if it can be inverted, which is an algebraic question that's not always easy to answer, this will give us what our orbit is, r as a function of phi. Let's look at one other way of doing this, which goes back actually to the force equation instead of using energy, just to see an alternative method. So here we have our generic force equation for our reduced mass. It depends on the second time derivative of position, of course. And then we also have some generic force law. In this case, F is possibly attractive or repulsive. It really doesn't matter, but it has to be central, so it's acting along that unit vector in between those. And I want to write this in polar coordinates. We already know that you can decompose this into planar motion for any central force. And last time we worked out what the general second derivative of a polar two-dimensional vector is. So let me go ahead and write that up on the board here. Okay, so just as a quick reminder here, the general second derivative in polar coordinates will have a piece in the r hat direction. Notice it depends on the radial acceleration, but also this sort of angular velocity dependence that comes from the rate of change of r hat itself. And then there's a piece that goes in the phi hat direction, which is perpendicular to that. We have our usual angular acceleration piece, and then a Coriolis type term, which depends on r dot and phi dot together. So we've kind of looked at that before. In our case, since we're looking at central potentials, this term is 0. And in fact, that's another way of getting back to conservation of angular momentum that I'll leave off for now. Over here, though, we can see that equating these and dropping out the r hats gives us a scalar version of our force law. And again, using conservation of angular momentum, we can replace this phi dot that shows up here with something involving L to get a second derivative of r directly. Okay, and here we can see the actual force law showing up, and then there's that centrifugal force as promised. Notice it's a 1 over r cubed force because it came from a 1 over r squared potential. And this is a second order differential equation in terms of r. Now again, what we're trying to get to is an orbit condition or equation, and this still has second time derivatives of r. I want to swap that out for some kind of spatial or angular derivative of r. And to do that, we're going to do something that's pretty common in these types of situations. We're going to make a little substitution, which is to define a new variable, lowercase u, don't confuse it with the capital U here, which is simply the reciprocal of r. And you can kind of see why that might be useful. I've got a 1 over r cubed here. I've got a 1 over r squared here. In the Kepler equation, for example, this u of r is 1 over r. It has something with 1 over r. Reciprocals seem to make a big deal here. Let's go ahead and make that substitution. And then let's see how we might be able to change this time derivative to an angular derivative. So first thing I'm going to do is, again, go back to my conserved angular momentum. We can see over and over how powerful that is, and still for any arbitrary force. And notice that I've got a dt and a d phi that are kind of directly related here. So maybe this is how I should think about transforming time derivatives into spatial or angular derivatives. So first off, let's notice that by a slight abuse of notation, but it works, I can rewrite a reciprocal version of this. It's got a ddt here by dividing out and then L over mu r squared dd phi. And then to connect with our previous notation, that's L over mu u squared dd phi. And so now I can see how to transform a time derivative into an angle derivative. It multiplies by some extra junk, but they're directly related now. Okay, so now what we want to do is try to write down this r double dot in terms of u's and primes, or spatial derivatives. So let's first write down what r dot is. This is d dt, the time derivative of 1 over u, but using this little switch around, we've got L over mu squared, or L over mu, u squared, dd phi of 1 over u. And the derivative of 1 over u is going to be a negative 1 over u squared, which exactly cancels the u squared here. That's nice. And then I'll have a chain rule time derivative of, not time, angular derivative of u. So we'll pick up a negative sign. The u squared that comes from the quotient rule here cancels, and we're left with u prime, where please note that prime here indicates du d phi. We're talking about angular derivatives now in place of time derivatives. We can then, of course, find the second derivative. It'll be the time derivative of the thing we just got. Okay, I'm going to use my usual trick again of swapping the ddt for something involving a dd phi. And just like before, some constants come through. This time there's no cancellation, but I do have a angular derivative of an angular derivative, which will just be a second derivative. And then the stuff out front kind of nicely factors a little, or at least it combines into a kind of nice way. And we're left with a second angle derivative of u. Okay, so maybe that's kind of convenient. We're going to see how good this is in just a sec. But this should help us write down some sort of differential equation relating u, which is 1 over r, and this angular direction, phi. So let's collect our main results over to the side, and then we'll finish this off. Okay, so just a summary here. Here's our scalar version of this equation in terms of radial motion, which we extracted by using the second derivative of polar coordinate vectors. I went ahead and just, in case you need them, here's the dr dt, d phi dt, and d phi dr calculations. You could also write that as dr d phi, I suppose, if you integrate, but it's going to be the same separation of variables. But you can see how nasty this is going to be unless we've got some very nice numbers or very particular symmetries involved in our central potential. And then here in purple is our last new bit, which says if I make the substitution to this new variable lowercase u, which is the reciprocal of the radius, then my second derivative, which shows up here, turns into a second spatial or angular derivative with respect to this u variable. So now let's go back to our Newton's law and see what this looks like in terms of u. Okay, so we'll start with our r double dot, which is now this negative thing. On the right-hand side, we've got f of r, which of course is now going to be f of 1 over u. So it'll be a little curious maybe, but it's convenient if your forces are reciprocal power laws. And then notice this piece that has an r cubed will just have a u cubed in it in the numerator now. And what I want to do now is basically divide everything by u squared and then make the coefficient of this u double prime positive 1. So first off, this first term is just going to be u double prime. This term, when I divide by the L squared goes away. The mu over mu squared also has a mu over here, which goes away. And then if I move this over, the negative sign will also go away. So I just get u, and of course the u cubed becomes a u after dividing by the u squared. This is kind of nice, because this particular combo of the second derivative plus the function itself shows up in a lot of places in physics. In fact, if this was equal to 0, which it's not, but if it was equal to 0, this is exactly the simple harmonic oscillator equation, and we would expect to get some sort of oscillating, maybe circular motion, some sort of periodic behavior to the system. In our case, the right-hand side is not 0. When I properly multiply everything over, I'll get a negative sign, And what'll that be? A mu, not a u. I apologize for the mu u issue. And then there'll be a 1 over u squared times f of 1 over u. Presumably, this whole combo is some known function, but this combo together of this sort of simple harmonic oscillator form set equal to some function of u is called the Binet equation. And this is actually a convenient starting point for a lot of different calculations involving, well, the Kepler problem for one, but also more general choices of central potential. You could, of course, go straight to here. After all, this is still a differential equation, and the solutions are still going to be given by these sort of messy square roots, perhaps. But the familiarity of this particular diffie-q is kind of nice. Okay, so we've now seen a couple different general results that can be applied to any central potential. Let's actually use the Binet equation to solve one very particular type of potential, which is no potential at all. What if I have a central force, which is just zero? So I have a free particle moving along. Mu could still be a reduced mass, I suppose, or it could just be a mass by itself. But what if this F, this force here, literally was the number 0? And by the way, in case you don't know F and instead you know something like R, you can, of course, exchange the F and R's with just some derivatives. Remember that force is just the negative gradient of potential. You'd have to be careful about the chain rule. It does depend on 1 over u. But actually, we could do that pretty easily, because if I take the derivative of this 1 over u, well, that's going to give me a minus 1 over u squared, which exactly cancels this 1 over u squared here and the minus sign that comes from the derivative. So if we use the fact that f is minus the gradient of u, as a side note, we can actually reduce this still further to just u prime of 1 over u. So it's even simpler if you write it in terms of the potential. Of course, you have to take the derivative, but that's not too bad. So again, let's look at the free particle, just as an example to wrap this up. And this is the case u of r equals 0. There's no potential energy at all. It's just flying through empty space. Well, the derivative, even if I do some 1 over stuff and take a derivative, all this stuff is just going to be 0. Careful, I'm not taking 1 over 0. U is 0, capital U, not the radius or lowercase u. But it means the right-hand side of this is 0. Okay, so my equation becomes u double prime plus u equals 0. And I just said how that's a very famous equation. It's the simple harmonic oscillator equation with a frequency of 1. So we instantly know what the answers are. I'm going to have u, which is a function of phi. Don't forget, these primes indicate not a time derivative, but an angle derivative, is going to be, let's say, some constant. I'll go ahead and write it with a cosine. Of course, you could write it with sine, or you could write it as a linear combination of sines and cosines. But the most convenient way is probably just something like this. Second order does mean I'm going to have 2 constants of integration, so I called that an amplitude and a starting phase. You could still rewrite this in terms of sines and cosines if you want, with 2 different amplitudes. I could have put a plus sign here. I could have chosen a sine instead of a cosine. It really doesn't matter to me, but this is a completely general form. Change the others how you like. We're not quite done, though. That's not r of phi. R of phi, of course, is just 1 over u. And if I reciprocate this, I'll have 1 over a cosine of some junk. Or, put another way, some sort of, I'll call it r naught. And by r naught, I mean the value this takes when phi equals your starting value. Cosine of that is cosine of 0, which is 1. So it's part of the reason I used a cosine. Times secant of phi minus phi naught. What does this equation look like in polar coordinates? Okay, so here's my x and y axes, but of course I'm really thinking about this as polar coordinates. Well, this is actually a straight line. Maybe it's a little weird to see that. To see it, you should probably multiply this cosine back over, and remember that r times cosine phi is x. You might have to distribute this, this cosine as a difference formula to write it as cosines and sines. But if you want to see that, we can make it more explicit. Multiply back over here, and I'm going to get the cosine expansion. So r times cosine of a difference becomes cosine of the first sine, cosine of the second. It'll be a plus sign because of what I chose there. Sine of the first times the sine of the second, and this is all supposed to equal some constant. And then when I distribute my r cosine phi is exactly x, and r sine phi is exactly y. And then these two terms are just two constants. So I could call this something like ax plus by equals some other constant, which is of course the equation of a straight line in Cartesian coordinates. Here in polar coordinates, it's a little bit easier to kind of think about this because the ABCs are a little iffy. Maybe they're related to intercepts or something. Here it's real nice. I'm just going to draw out a little distance r0 at a little angle phi naught, and then the line that is perpendicular to that little segment, that's exactly the line that we've got. Notice it's parameterized by the point of closest approach, which is usually kind of nice. And it's also parameterized by this phi naught, which is what sort of shifts this line, rotates it around the origin. Were we expecting that? I certainly hope so. If we have no potential energy, I expect the trajectory of a free particle to be rectilinear motion along a straight line, even if it's written in polar coordinates. At any rate, I think that's a pretty good wrap-up. We were able to take our values or our conservation laws as differential equations. Yeah, we could have used them. They're a little messy. But we get this other sort of differential equation that comes for more or less for free, the Binet equation. And we even solved it in a particular case of a free particle. Next time around, we'll see what we can do for the Kepler law specifically. QED.